Welcome back, everyone. And yes, I'm finally back. So today, I think I wanted to actually start a new kind of series, and that's going to be a linear algebra series. However, it's more special than just linear algebra. In fact, more specifically, it's going to be abstract linear algebra. That is, we're actually going to closely follow the book Linear Algebra Done Right by Sheldon Axler. So I have it right here. It's a very good book. Highly recommend it. Um, And so, yeah, we're going to be closely following this book. Today is just going to be pretty light content-wise. We're kind of just going to introduce the basics. And so, it's highly recommended, again, that you have this book alongside you as you watch. And in fact, I'm also considering making another series alongside the series, although, well, it's not completely related, but it's of a course that I recently took regarding multivariable calculus. However, this goes into n dimensions, not just 3 dimension, as a standard multivariable calculus course would. And so some of the content there is quite interesting, so I might go through that. It's also proof-based. So why don't we get started? So the basics. Well, I assume that you've already taken a first exposure class to linear algebra, and so this, I will kind of leave out some of the very basic gaps. However, let's just get the basics out. So I'm sure you've already heard of the notion of a field. For our purposes, we're going to say fields denoted like this, and doesn't look like we're writing so well. Field. So field, for our purposes, is going to be the complex numbers or the real numbers. And you'll see in this course, we use the field rather than just real numbers so as to be more general. The whole idea of abstract linear algebra is that we're not giving coordinate proofs, okay? And so we're going to stick to very abstract ideas. In fact, we're going to leave out determinants till the end because this will make the proofs, and hence, actually, this is why Sheldon Axler named it Linear Algebra Done Right. The right way to teach linear algebra, in his opinion, is to leave determinants to the end, determinants. And so, okay, these are our two fields, the complex numbers and the real numbers. And so now we define, and well, there are certain axioms that both of these sets hold, both of these fields hold. Complex numbers, well, commutative, associative, closed under multiplication, etc. There are numerous properties that these sets have. We won't go into those. Those are they're listed out in the book a bit, but they're not. It is assumed that the viewer knows about these. But yeah, there's nothing too meaningful there. However, now let's define the notion of a vector field. So vector field, notice that it has field in the name, and in fact, over a certain field. Over R, you see. So, okay. Now a vector field over R, I'm sure if you've taken a first course in linear algebra, which you assume to have taken, you've heard of what a vector field is. In fact, you've covered that probably later in linear algebra. You've probably gone through matrices first. Anyway, a vector field over field F. A vector field, and throughout this course, we're going to be denoting it V, so vector field V, like this, just capital V. It also satisfies a multitude of properties, very familiar to those of field, and in fact, many of those follow from the fact that it's over a certain field F. Now, we're normally in first exposure to linear algebra, we're dealing with vector fields like Rn. So examples, Rn and Cn, complex numbers, real numbers. So in other words, the list, in fact, the list I have to define reversely, it's just a list of, so a list of length n is kind of like an ordered pair of n elements, so that's a list. Now Rn, again as a review, it's the set of all lists where the components are real numbers, are a member of the field real numbers, and it's analogous for C. The components are a member of complex numbers. Okay, and so these are the two examples of fields you would use in your first linear algebra class. Primarily Rn, right? So Euclidean space. So yes, vector fields. Now, I think, well, first of all, let's elaborate on this abstract idea. So we're going to do a few very basic proofs in order to show the abstractness that we're going to be using throughout the course. So for example, let's say, again, the vector fields satisfy a multitude of axioms, but we can build on those axioms. For example, one of the axioms is that there always exists an additive inverse for each element. And so we can add on to that. In fact, those inverses are unique. So uniqueness of inverses. So suppose we have a vector field V, and suppose we have, now when I'm writing things on the board, it's very like kind of the sketch of the proof, because I'm saying a lot of what I'm a lot of what should be written. That's very important to note. So take any element, call it x in our vector field V, and suppose there are two additive identities to this x. So suppose it's fine. B, C in the vector field are two additive. See what I mean about writing everything on board? It gets kind of tedious. Okay, then it must hold by definition that x plus b equals the identity, and the identity is defined as the zero element, so 0, and we have that x plus c is also 0. Okay, but now let's use associativity. That is, consider the following sum, x plus b. Well, let's first write b in a certain way. We want to show that b equals c again. And so b equals, well, let's see. First we have b plus, in parentheses, x plus c, right? Because x plus c is just the identity element. The identity element plus any element in the set is the same element, is that element. And so this is equal to, by associativity, regroup these parentheses, b plus x plus c equals, well, by commutativity, this is also the identity element, and so b equals c, as desired. Aha, that's why it was acting funny. Okay. So that's one quick proof. I guess I can write the nice little box, although this was kind of a meaningless, very simple proof, just to get an idea of what we're going for. And I'll actually let you show uniqueness of the identity. It follows a pretty much analogous argument, but with the special property for the identity. Okay. And maybe let's do one more, which is a bit different. It involves a different axiom of vector space. Suppose x is in V, then show that 0x. This is actually a good example because it illustrates my point here of abstractness. A common mistake is that one would write x as a list, x1 through xn, but that assumes that we're using one of these vector fields. However, that is an assumption, and so since we're dealing with abstract linear algebra, we want to be more general. And so to be more general, we only use the axioms of a vector field. So let's do this. Clearly 0x equals 0 plus 0x. I shouldn't say clearly, that's often a mistake one makes, but we can explain this very easily. 0 is the identity element, and so 0 plus the identity element is just 0, okay? It's kind of meaningless to explain, but it's still important given how delicate these proofs are. And so by the distributive property, which is another axiom of vector field, this is equal to 0x plus 0x. And now we add the additive inverse of 0x on both sides. Again, I say we've proven the uniqueness of inverses. And so that implies indeed that 0x equals, well, that an element plus its additive identity is equal to the identity element, which is 0. And so QED. Good. Okay, and let's get that out of the way. And I think we're ready to get to the more interesting stuff, as you might say. That was just a prelude. And let's see, how are we doing on time? 11 minutes, okay. So now we're gonna briefly look over subspaces. I'm sure you've dealt with subspaces in your first course of linear algebra. First exposure, that is. You might have not taken an actual course like me. And so, okay. Subspaces. These are important. Subspaces. So, suppose definition. So, I'm leaving out a lot of words again. Subset of the vector space V is a subspace. It's a definition, so I'm not going to write if and only if the following three results hold. That is, I guess in words, a subspace of a vector space V is a subset of a vector space that is also a vector space. That's really all it is. But this is actually this definition is more precise because I guess, well, it's more precise because it leaves out some of the properties you would have to prove normally for a vector space. Because, for example, if you look at associativity, it's automatically associative. It's automatically associative since it's in a vector space, right? And so we can leave out the proofs of some of those axioms. Well, essentially there are three conditions that are sufficient, right? In fact, they give exactly the definition of subspace, and these are the three conditions. You probably recall these. Well, closed under addition. So close under ... scalar multiplication. And the easiest one, most likely, contains the additive identity 0. I mean, yeah, the additive identity 0. So these are the three conditions that we can strip away from those, like, 10-something conditions or whatever, for a vector space. So this is how we define a subspace, right? Okay, So, in fact, funnily enough, I have a very old video on my channel about subspaces. It's all right. It goes into examples of some subspaces, but here are important ones. Let's look at the vector space v equals Rn. We have the 2D coordinate plane. We need these subspaces to go. Okay, well here we have n equals 2, of course. We have the coordinate plane. We need the subspaces to go through the origin. So for example, lines, that's a valid those are valid subspaces. So U1, why is that? If you take any vector on the line, multiply it by some scalar lambda, it stays on the line, by definition of line. Well, the vector space, the largest subspace of a vector space, is that vector space. The smallest one is just the 0 element. So just 0. So those are the only types of subspaces for R2. But you can kind of generalize this to Rn. You'll also have subspaces that go through the origin, subsets that go through the origin. In particular, R3, you have the addition of planes, and of course, the vector space itself, etc. So, that you've surely gone through before. Okay. Well, I guess that is about it for subspaces. Let's see, we could give a more interesting example of a subspace. Let's go with, well, here's an easy one. In fact, it's a plane. The observant viewer might notice it's a plane. Let's see, x in all x such that x equal to x1. Let's be more specific. So this list, we're in R3 such that, or yeah, this is the best way of putting this. F. I forgot to define this, but this is like, if you write F3, it's the set of all, well, this can either be the R3 or C3, essentially. Complex numbers, three-dimensional, real numbers, three-dimensional, right? See, let's take, for example, 4x1 minus 2x2 plus, so this depends on if we want to make this a subspace or not. So let's make it a subspace. I just revealed it. Is this a subspace or not? I would say yes. Okay. Why is that? Well, first of all, is the 0 element in there? Well, let's see. x1, x2, x3 equal to 0. Indeed, that triple gives 0 equals 0, and so it's a valid point in that set. Also, well, if you add any two elements in here, so let's say x plus x prime, where x prime are in field F3. Well, let's see, then they both satisfy this, and so, well, what we want to consider really is x1 plus x1 prime. I guess I have to write this out then, but x2 plus x2 prime plus 3 x3 plus x3 prime. And then you can distribute these out, and you'll get 0 plus 0 equals 0, and so indeed close under addition. And finally, scalar multiplication, same deal. You get some scalar lambda times this expression, which is 0, lambda times 0 equals 0, etc. That's good enough for examples. There are good exercises in the book, though. So, okay. Now let's get to the even better stuff. Let's look at sums of subspaces. Definition. Let's say, what notation shall we use? Let's say U1, U2 are both subspaces. Let's use that notation. Yeah. These two are both subspaces of our vector space V. Okay. This is really good notation. Okay. Let me just make sure I'm using the correct notation. Yeah, I mean, in the book he lists it out in words, which you can because it's typed up. Okay. We'll just use this non-rigorous notation because this just says they're subsets of V, which isn't specific enough, but we'll say in words these are subspaces of V. Okay. Then, so define U1 plus U2 equals, so definition, we usually write this. We have all U1 plus U2 such that U1 is in capital U1 and U2 is of course in capital U2. So we want to prove the following statement. So proposition U1 plus U2 is the smallest subspace of V containing the well, we could, this would be containing both of the subspaces, but to be more general, we write U1 all the way through UN. So we can have multiple sum containing all of the UIs. Okay. Since we're already breaking 22 minutes, I'm going to continue this proof and the proof of some other important facts in the next video. I'll see you then. Oh, I almost forgot.